In a previous video, we looked at missingness, different types of missingness. And so in this particular video, what we're going to do is look at how do you deal with the missingness. In our previous video, we talked about how mostly if you have large data sets, you remove the information that is missing. But we can be a bit more strategic on how we deal with missingness. So we're going to look in this video about forecasting models, neural networks, classification, cluster models. What do you do specifically in each situation? So just to recap from the previous video, you are missing completely at random if the reason that the information is missing is independent of the data itself. So the reason for missingness is not related to any particular variable in your data set. If you're missing at random, then the cause of missingness is related to the characteristics in other variables, not the variable that is for example, typically we look at what's missing. Missing might be the label, the classification, or it might be a measurement that we're using to predict something. If it's because of other variables, so there's something else that a condition that we are representing in our data set, but it's not that variable itself that's causing the missingness, we're missing at random. If it is the characteristics or the measurement itself that is the reason it's missing, then we're missing not at random. So what do we do in these scenarios? All right, so how do we deal with missingness? There are different ways to deal with missingness we referenced in the previous video. You can impute or replace the missing information. So in this particular data set here, we're missing the marital status. I don't know why all my circles are now off, but we're missing the educational status for one person. We're missing the bank balance. So we can see this information is not there. Let's suppose that we want to predict or identify the characteristics, the patterns. Can we predict who's going to buy? And this is the banking data set we looked at in a previous video. Are they likely to buy a GIC? Well, is marital status a predictor of whether they would buy that GIC, education, bank balance? Can we detect this pattern with this information missing? So some of the options are to replace that missing data with the median. So the bank balance, we could say, okay, well, this is 50% are higher than this number, 50% are lower, so let's put that number in. Or the average, what's the average of the bank balances? In both of those cases, because you are putting information into the data set, you are reducing the variability in the data that allows us to identify the pattern. You also can create bias in the data set if we are trying to identify whether or not a variable like marital, like the bank balance, is statistically significant. We're causing it to not be statistically significant by putting in the mean or median. If we have a large amount of missing data, then that variable becomes insignificant because there's not the variability that we can attach with these different things we're trying to identify. We can also randomly sample values from the variables. So we could, if we're trying to figure out marital status, we could have it randomly decide whether or not to put married or single into that spot, or for education, primary, tertiary, secondary, we could randomly have it pick one of them. So these are methods to impute or replace the missing information. We want to be careful about when we do this and talk about when it's appropriate and when it's not. Another alternative is to take that whole row. So you can see row 5 here, this person age 30 in management, that is missing information. Do we just drop that whole row? Now we want to be careful about dropping data from our data set, because if the missing information in row 30 is about marital status, and we're not going to use marital status in our algorithm or statistical model at all, then why would we get rid of that row? Because the fact that it's missing doesn't matter to us. So what we often want to do is to create a smaller table first of the variables that are relevant to our model, and then we can use the drop NA to drop rows that are missing information. This prevents overculling or removing rows of data that happen to be missing information, but they're not missing anything that we really need. There are even other more complicated methods for dealing with missingness. You can develop, there are, for example, Bayesian models that can then model the missingness and create a statistical model of the likelihood of missingness and help to kind of address the issue with the imputation where we're just putting in a random number or we're putting in the average and actually creating a bit more informed values to replace with. So we're not going to get into the Bayesian models, that's more complicated, but we'll talk about dropping and then the imputation in this video. So we're going to look at some different models: forecasting, regression, classification, cluster, and neural network. They serve different purposes. They often use the same type of models. So for example, in classification, there's a generalized linear model, which is a linear regression. So they are using some of the same components, but for different purposes. And so how we deal with the missingness is going to be different depending on our scenario. So let's start with short-term forecasting. So I want to forecast the number of complaints. I'm using a moving average. That moving average adds up, let's say, the previous 3 periods, and then uses that to calculate the next period. So what if we are missing period number 3 and 55? What should we do? Well, the key to know here is that whenever you are deciding how to deal with missingness and choosing a method, make sure you know the assumptions of the model that you are using. So for example, a moving average assumes stable data, but with a little bit of variability. A naive model assumes very stable data. Whatever happened in the past continues on in the future. So if I look at my data set here and I say, okay, well, if I want a moving average, that's going to assume that there's a little bit of change. So how we replace this missing information, how we impute, needs to match that assumptions. So I can't just take in and throw into this blue box here a naive approach, just copy 65 and put it in this hole, because that changes the assumptions of the model. We're assuming we're stagnant, no movement from period 2 to 3, but the rest of the time we're going to allow for a little variability. So we want to make sure we maintain and protect the assumptions of the model, that they're consistent as we look at filling in the missingness if we're going to fill it in. So different models have different assumptions. Weighted moving averages, they assume relative stability, but it puts a greater weight on the more recent data. So again, slightly different than the assumptions of a moving average, because it's allowing a little bit more variability, and the moving average allows a little bit more variability than the naive. So we want to be consistent. All right, so if we had no missingness, okay, so we knew period 3, then we could forecast period 5 using 4, 3, and 2, so a 3-period moving average. And then we would get that period 5 had a, number of complaints of 59. Notice if I use other methods to fill in, if period 3 is missing, if I replace period 3 with the average of periods 1, 2, and 4, then in that case, then the forecast I get for period 5 is now a 61. Okay, now these numbers are all ranging 55 to 65, so we are talking just 1 point off. But think about these in terms of the 10,000s, the 100,000s, if these are dollar values, right? Even that little bit can have a big impact. And so recognize how imputing with the mean here in this scenario does skew the next forecast to be higher. If we impute with the median, then the median of periods 1, 2, and 4 is 60. It makes it slightly lower for the forecast for period 5, but still higher than what it would be if there was nothing missing. So when it comes to the mean, recognize that the mean is going to be impacted by extremes. So the fact that period 2 was much higher than period 1 and 4 is going to skew that mean and have an impact on our forecast when we insert the mean for that missing data point. If we randomly pick a number from period 1, 2, and 4, let's say we happen to pick a number that is that is 58, that is the lowest of the three, you can see that that one happens to give us closest to what if there was no missingness, but it's just a random pull. So we could have instead pulled the higher number, 65, in which case the forecasted number would be higher than the mean and the median method. If we remove and simply ignore period 3, then what we get is a forecast of period 5 for 61. Now, none of these are great because we notice that with the actual data, it's a lower number. But the other consideration we have is that we have different assumptions in these different methods, but also this is supposed to be a forecast based on 3 periods, 3 years. If we, for example, just struck period 3 and did periods 1, 2, and 4, then our forecast for period 5 is not actually a 3-period, 3-year forecast, because it's based on a 4-year period if we just simply remove it. So when it comes to short-term time series forecasting, instead of using one of these imputation methods or deleting the data and then no longer having a 3-period, instead looking at 4 years of data, what we do to impute the missing information is we maintain our methodology by doing a moving average, and we do a moving average using periods 0, 1, and 2 to impute period 3, and then we use that going forward to forecast our period 5. That maintains the consistency of our assumptions. We're using the same single forecasting method of a moving average throughout. It allows a more informed imputation to fill in that spot. We're not arbitrarily skewing it, and we are not then turning it into a larger, more period model than we stated. So with the short term, we want to use the same forecasting method to impute. That'll avoid the bias. Now, what if we are forecasting more medium length or long term? So a SARIMA or a RIMA model, a profit model, or maybe we're simply doing just a line of best fit for a long-term trend. When it comes to long-term trends, right, you can have a linear one. Over time, the number goes up, or over time, the number goes down. Or you can have a polynomial. Polynomials of degree 2 go up and then down, or down and up, right? So it looks like a U. There are also growth curves, logarithmic curves, exponential curves. We go into these and all these in a bunch of different videos. And so we fit these models. So what we do is we take our data over time. So here's time on the horizontal axes. Here's what we're trying to predict that's on the vertical axes. And so if this is the number of complaints, we could, for example, use period 8 through 15 to forecast period 16. Well, what if we didn't have this one in the box? Well, in this case, if you simply remove this, then it still is able to come up with this same line of best fit, because it just says this information is absent, but it's still trying to minimize the distance between all these points. So we don't actually need to impute a mean into it, because the challenge, of course, is that if you imputed the mean and it had this downward trend, well, that mean or that median would skew it because it's based on time, and over time it's going down. So in this case, we're kind of in the middle, but if I had to replace this one right here with the mean, that would put this data point right here and then would entirely disrupt or bias this forecast. Same thing with the median. If it was the median of these values, it would still be up here. And if we were replacing this lower one, it would skew the trend line, and the trend line would be much flatter instead of downward sloping. So in this case, if we're doing long-term trends or we're doing, then it's better just to leave the data point off. Leave it empty, let it find the line of best fit without it, so that you're not then taking that trend line and flattening it out instead of going downward because of where the missing happens to be in time. If the missing happens to be in time in the middle and it's a linear trend line, it has less of a bias. If it is at the beginning, it would pull the whole trend line down because the average or median would be here, and we'd be pulling that data point and then flattening out that line. So because of this time component, it's better to remove it and just have that information be absent from the model instead of imputing something in it. So medium and long term, we leave the missing value empty because that time component that fits into whatever shape curve, having an average or a median has varying impacts of bias depending on where you are in that curve. So better off just to leave it. Okay, what about a regression model? All right, so in our regression model, instead of time, we have some other variable or variables that we are using to create our forecast. So I'll just temporarily move my face here. Okay, so in this case, we have our number of break-ins. We're trying to predict the number of locks that are sold, and we are looking for this pattern or relationship. It's similar to that linear trend. It's just instead of time, we have some other variable. Well, if our focus is on statistical significance, that is, how much does the number of break-ins and the change in the number of break-ins impact the change in the number of units sold, we want to be careful about imputing data, because if we go in and put in an average or a median or randomly generated, then the problem is, as we stated before, we're going to make a variable that might have been statistically significant. So number of break-ins varying may have been a good predictor of the number of units sold, but because, depending on how much missing information we have, if we have a lot of missing information and then we impute, then that variable becomes insignificant. In this case, what that would mean is that would be like with the linear trend, we just end up with a horizontal line, which means we can't use in the linear trend time, or in this case, the number of break-ins, to predict this value. If you have multiple variables, so you have a multiple variable regression, can't put it on a scatter plot because there's multiple variables being used to predict, then what happens is that when we go to analyze it, the variables that would have been statistically significant, we would have identified as being important in having an impact, are now then showing as not being impactful. So for example, here we have a logit regression. So logistic regression, we are predicting a binary variable. Yes, no, buy, don't buy. Here, this case, we're trying to predict whether or not it's a Gen 2 penguin. So our regression model has these variables. But if we're missing a lot of information, and then it's going to make these variables insignificant when they otherwise would. So if your focus is on which of these variables is statistically significant, don't impute, don't put values in for the missing information, because you're going to create less variability in the overall data set for these variables, and they will become insignificant as we look at which variables are used to predict it. It's better to have nothing, because then at least we get the variation, and it's not that that variation gets muted by the fact there's a bunch of these records that have no variability. So when it comes to multiple variable regression, we have videos on that. We talk about logistic regression, Poisson, and linear. All we have is more, in this case, we're looking at more than one predictor or independent variable. If you're doing these different methods, so I'll just snapshot from some of our other videos. If we're doing it with a focus on statistical significance, we use statsmodel.formula.api. We'll call it SMF for short. And you can see here the coding is a little bit different than if we're using our sklearn methods for classification models or our neural networks. And so here it is SMF logit if it's yes, no, binary predictor. And then you see a little squiggle, and then these would be the variables we're using to predict it. We call the model, we fit the model, and then we get the output. And the output you see looks like this output here. If we're looking at some of the other models, like the Poisson regression, you can see similar wording there. SMF.Poisson, what's first is what you're trying to predict. In this case, it's counts, so numbers of things, where they can't be partial numbers. So in this case, this is police stops. And then we have our variables being used to predict it. You can see here we can have multiple variables by simply putting one variable name plus another variable name. Just a warning, the stats model formula.api is unhappy if your variables have spaces in them. So take your variable names, make them short, make them all one word. Otherwise, this package doesn't like it. The other thing you can see here, here's a linear regression. So here we have smf.ols. This is the variable we're trying to predict. In this case, it is a measurement. Earnings per share can have fractions of numbers, and we are using, in this case, 4 different variables to predict the earnings per share. So you can see how the formatting is similar. It just depends on what type of model you have, whether you are dealing with binary is what you're trying to predict, whether it's a count, or whether it is a measurement. In all of these cases, you'll ultimately end up with an output that looks like this. The focus here, just moving my head again, is to determine which of these variables are statistically significant. We're looking for a p-value less than alpha, less than 0.05 typically, to tell us how much these particular variables have an impact, and that's this coefficient here, how much impact they have on whether or not something is a certain classification or measurement or count. If we are focused on prediction and assuming we have lots of variables, so which particular variable is statistically significant is not important. It's just that we have lots of variables, and within them there are going to be ones that are going to have a significant impact and others don't. So it's okay if one particular variable becomes a little bit less statistically significant, has a little bit less impact on the model, then we can impute. So we can impute using median, mean, or random sampled values. So how do you decide which one? Well, if you are not concerned with outliers, so extreme values, then the mean is probably the easiest and most common. If you are concerned that you have some respondents, some data in your data are going to have extreme values that could skew the model, then the median might be more appropriate. If you are certain that you have MCAR, so just to go back to the different types of missingness, if you are confident that your missingness is independent of the variables in your data set, the variable that has the missing information, the variables that are being used in the model that don't have the missing information, if you're certain that the reason it's missing is not related to any of those, so missing completely at random, then you can do the random generation of that data. So if you're not certain that you are missing completely at random, that it could be due to the value of your variables, then you would use the mean or the median. So then it's going to be tied more, right, to the values of the variables to adjust for that fact that that missingness could be tied to the variable itself. So if you're focused on prediction, you're not looking at statistical significance of variables, you have lots of variables, then you could do imputation, and only if you are missing completely at random should you be using that random sampling. You can also choose to use to drop the data instead of imputation with your regression model. We look at how big is the data set and how much of the data set is missing information. If your missing information is just a handful, so let's say you have thousands of records, you have like 5 of those records that are missing information, dropping those couple rows probably not going to make a huge difference unless there's something special about those ones that are missing. And that comes back to, sorry, as we go way back, is that if they're missing not at random. If they're missing this is because they were certain values. So there's a certain group that we just can't get information from. That particular group is significant in determining whatever we're trying to predict. And so in that case, that's where you're going to have a problem. That's that missing not at random. If it's not that though, then if you have just a small number of missing and they are missing completely at random or missing at random, you could probably just delete those couple rows. If you have a large amount of missingness and it's missing at random, then we start to have issues in terms of that statistical significance of variables and skewing it. And so that's why if we go back, here we go. Sorry, I don't even know where we are on this list. There we go. Then you can start looking at that mean or median, which tries to compensate for some of that that missingness that is in our middle scenario, missing completely or missing at random. All right, so if you are going to get rid of, you can what you can do is you can do your replace. Sorry, if you're going to impute, you can do your replace, and you can replace it then any of the NANs. So I'll just move my face. So they'll show in your data set as an empty cell, and you can then use your replace and mp.nan. So we're using NumPy to replace those NANs with, and then you could have it replaced with the median or the mean. We said that, so if you are doing regression with sklearn, where you are not focused on the statistical significance of variables, then you can do this regression with this Python code that you see here. So here we have sklearn linear model. So if we're doing our logistic regression, call the model, fit the model, predict. If you are doing Poisson with sklearn, we have Poisson regression, and then same thing, you call the model, fit the model, predict. And if you have linear regression, so we are trying to do a measurement, then we're using linear regression, call the model, fit the model, predict. So you can see here the Python code if we're focused simply on predicting, and logistic regression, predicting yes, no, binary, buy, don't buy. Poisson is going to be counts, number of birds, number of cases, and then linear regression is for measurements. Right, we're trying to predict a dollar value, we're trying to predict a height, those types of things. All right. So if we're doing regression and we care about statistically significant, we drop the row with the missing information. If we're focused on prediction, we can impute or we can drop.